Hey everyone, welcome to the tutorial that you were waiting for since you started using Max, basically. So this is what we're going to achieve today. I think today maybe it's going to be split into sessions, but let's see what we manage. So this is something that I call the point cloud, and basically is a bunch of vertices, so we can call them particles, that are connected with lines as soon as they are close enough, under a certain distance. So I already made this patch something like 5 years ago, and I also made a video tutorial about it, but I don't know what was wrong with me at the time. This thing is really creepy, so here's a sample.
Oh yeah. It's actually weird. Sorry, this is so messy. This tutorial is so messy.
So yeah, I don't know, I was drunk. I mean, what's the matter with me? I feel like I'm a totally different person after 5 years. I don't know who this guy was. So to celebrate that I'm a different person, now I'm doing the tutorial again, but this time using a very different technique. So basically using the GPU for the whole algorithm. So it's much faster, we can really achieve very cool result with that. I've just started to scratch the surface of what we can achieve, but I'm going to put out some patches in the future that use this technique. So without further rambling from my side, let's dive into it. So first things first, I'm going to get my Jitter world, as I do always. World plus camera. We're not going to need the size of the windows, so we can delete that. And great. Then what else we need? Well, we need a matrix that will give us the positions of the particles or vertices in the world. So we're going to do that using a JIT noise for the moment. So just simply we're going to get, I don't know, like 1000 vertices, because we're going to connect this to a GGL mesh. Let's bang it. And cool. And then basically we need a GGL mesh. So GGL mesh that draws to game. That's the name of my GL context, which is a draw mode. Set to points, and color maybe white. That's it for the moment. So let's see what we get if we just do this. Cool, so we get a bunch of particles, bunch of vertices represented as points. They're a bit small. Let's make them bigger by giving to this GGL mesh the attribute point size 10 or something like that. Good, now they're much bigger. As you can see, they're all in the positive quadrant of our world, because the JIT noise only gives us numbers between 0 and 1. So we can use a JIT.map object to remap this range. So from 0 to 1, between -1 and 1. So now they're going to spread between -1 and 1 on all the three axes, x, y, and z. Good, so now the rest of the algorithm is going to take place on the GPU. So we're going to create a shader that is going to take these points as inputs, checking which ones are close to each other, and using a geometry shader, we're going to draw lines between those objects. So we're also going to use geometry shader, which is pretty cool. So let's do it. We need a GGL shader, as I said. So jit.gl shader object which draws to game, and as a name of shady lines, and file, let's give it a file name. Let's call it shadylines.jxs. That's the format Max uses for shaders. So I double click on it and it opens it here. Now I'm going to save that on my desktop as the name that I choose, so shadylines.jxs. Actually not as a txt, but as a JXS. Cool. Now when I double click on this again, it's going to open it on Visual Studio Code. So now I just have to select the GLSL programming extension, which can be downloaded here from the packages of Visual Studio Code. And you can use the editor of your choice. You can set up the editor on the Max preferences. And cool, so that's the default shader that is open when we first create a GGL shader. This is what Max gives us, it's just a default shader. Now, if we were to apply this shader to this object, it will not work anymore, because this object uses a geometry shader that expects as an input lines adjacency, but we are actually drawing points, and is also sending us output triangle strip. It's completely not what we need, but let's attach it anyway to the object. So we're going to say to the GGL mesh shader shady lines. And as I said, now it doesn't work anymore. So cool, we got to work a bit on our shader. So let's open the shader file. Let's call it connect close vertices, something like that. The description and the name is also basically the same. Connect close vertices. Cool. And we get as inputs for the moment the position, the model view projection matrix, and the color. This is all stuff that we need, so it's perfectly fine. So let's check what we got in the vertex shader. So the first shader that we got here is the vertex shader. As you probably know from my previous tutorial, and if you don't know, I encourage you to check my previous tutorial on shaders. Link in the description. Basically, a shader is composed in max of maximum 3 elements. There is always a vertex shader, there is always a fragment shader here at the bottom, and there can be in between those two a geometry shader, but it's optional. And by default, max includes a geometry shader. So it's not always useful, depends on what you need to do with your shader, but in this case we are going to use the geometry shader, so it's cool that it's there. So let's just try to achieve the point to which we were in the beginning without the shader, so we just want to draw the particles as dots on our window. So what we're going to do is we are going to modify the geometry shader and say vertices out to 1. Instead of as an input type lines adjacency, we are going to say points. And there is a list of input types that we can use with a geometry shader. This is you can find it online if you Google for like geometry shader input types. So since we are in draw mode points with the GGL mesh object, we have to use input types points because we want to use points as an input, and then as an output we actually want to output something that is called line strip, which means we are going to output lines. So we get as input points and we're going to output as an output lines. So actually I say that we want to simply recreate what we got in the beginning, so we are going for the moment to set as an output also points. So we simply get 1 point as input and we output 1 point as output. Now let's actually change also here where it says layout. We have to say which type we get as an input, which type we get as an output, and max vertex is 1. So we get 1 vertex as input as a point primitive, and we want to output also a single point primitive as an output. Okay, cool. So basically what we need to do is to simply delete all these other 3 emit vertex. So we remain only with these 3 lines of code and then end primitive in the main function of the geometry shader. So this GL position is a variable that is inside the geometry shader itself, and we have to write to it to set the position of the vertex that we are outputting. And this is simply going to be as our input position. So this is GL_in. This is a built-in input variable that the GLSL provides for us and contains the position of the vertex that we output from the vertex shader. So we are simply assigning the position of our output vertex as the position of our input vertex. Why there is written 0 here? Because actually in a geometry shader, the input from the vertex shader is actually an array, as you can see. And this is an array because we could also use different primitives as input, for example lines or triangles, and in this case every vertex of this primitive will be part of this array. In this case we just have 1 point as an input, so the array is only comprised of 1 element. Since the primitive point is only 1 vertex, so this is always an array containing 1 single element, but it's nevertheless an array. So we are getting the position of the first and only vertex we input from the vertex shader, and we are assigning this as the GL position output of the geometry shader. And the same thing we do with the color. Then we emit this vertex, which basically means, okay, send this vertex to the next stage of the rendering pipeline. And actually we also want to enter the primitive because we said we only got 1 vertex. Good. Then we go on to the fragment shader, which is simply setting the color for this vertex on our screen. And we use the color that we assign to the shape here, color 1111, so white. We're going to use this color, and we are setting the color output as the JIT input color. The JIT input color we get as an output from the geometry shader, which in turn was receiving it as an input from the vertex shader. So it's all passed down from the vertex shader to the geometry shader and then to the fragment shader. So let's see if this actually works. Let me save that. I'm going to, oh yeah, as you can see, it's already working. So it's representing the dots as squares, because by default this is how they're going to be represented if we don't change it. In order to have them represented as circles, we basically have to do it manually inside the shader, because now we're using a custom shader for the GGL mesh. Before it was using the default shader before we attached another shader. And so we have to recreate the effect in the shader ourselves. And this we can do it simply like this. We can say if the length of GL point chords, and this is also a variable that is inside GLSL by default, minus 0.5 is greater than, let's say, 0.5, then discard these fragments, so don't render these pixels. Let's see if this works. Yeah, exactly, so it worked. If you want to have these circles bigger, we just need to make this number bigger, and then it's going to look more and more as a square. Exactly, so 0.5, and they will look as little circles instead of squares. Perfect. So now let's get finally to our algorithm. So we need to find a way to get the distance between one particle and all the other particles. Okay, so one single particle has to iterate through all the other particles and check how far is she or it from the other particles. And in order to do that, we can do this with a for loop inside our vertex shader. So once we find that this particle is actually close enough to the particle the vertex shader is currently processing, then it can send to the geometry shader the position of this particle that is currently being processed, plus the position of the particle that it found that are close enough to get connected with lines. So this is exactly what we're going to do. So in order to iter through all the other particles, we need to create a buffer object, which also works as a texture buffer. So let's create it, GGL buffer. This is a new object that you have if you have installed the GL3 package and activated it. And let's give it a name. Now let's give it a type. So we want to that this is a position buffer, because through this buffer we also set the position attribute in our shader. So we're also going to set this position value that is used to know where the particles are. And then we're going to say text buff 1. So this is now also a texture buffer, which means we can iterate through it. So let's connect here to the JIT_map object. So it receives a matrix as input. And this is not directly a GPU object in the sense that it doesn't accept textures as input. It only takes matrices, because it sends data from the CPU to the GPU. So it's not directly an object like GGLPix that only works on the GPU. This object actually transfers data from the CPU to the GPU. So we are now filling the GGL buffer object with this position, which is exactly the position that we are accessing from within our shader in the vertex program. Cool. So now let's create our for loop. So inside the vertex shader, so our first shader, the vertex program, we have to say for integer e equal to 0. And then we have to decide how many particles we want to iterate. Probably we want to iterate the whole buffer, so to check all the particles. So let's create here a variable. Let's call it iterations, so how many iterations we will have. For the moment, let's set this to 1000, which is the number of particles we got, because we say JIT noise 1000, so it's going to fill this buffer with 1000 vertices, which in turn means that we got 1000 particles. So I less than iterations, I plus plus. So we're going to iterate for all our particles, and what we got to do for all our particles, we got to get vector3 containing the position of all the other particles, because this particle is being processed at the moment and is going to check how far it is from all the other particles. So we need to get the position of the other particles in order to calculate this distance. So let's say other position, let's call it. So it basically means the position of the other particle. And we're going to use the function texel fetch, which used in conjunction with a one-dimensional buffer object is going to give us the elements in that buffer. We could have also used a texture and access a texture, but why use a texture when we can use a buffer object, which is, I think it's faster. So we need the name of our buffer that we didn't connect yet to our shader. Okay, we are accessing the position, which is filled through this buffer, but we also need to declare this as a texture buffer. So we need to create a new parameter, param, name, let's call it post buffer, type, it's going to be an integer because texture in Max are declared as integers. Default 0, so this is the only texture we got attached to this object. And then we need to bind it, so bind param post buffer to which program? To the vertex program, so VP. Cool. Great, now we need to declare it as a uniform, that's a uniform. And this uniform is of type sampler buffer, because this is this type of the buffer inside GLSL. And we give the name that we chose, which is post buffer. So we are now fetching post buffer using I as an iterator. So great, other position now contains the position of the particles one at a time. So we iterate through all the other particles. Now we have to get the distance, so let's get the distance. So the distance is simply a float. Let's call it dist, and this is equal to the length of our position, so position, which is a vector 3, exactly, minus other position. So the length of that is our distance. This is simply how vector math works. So now let's say if this distance is less than a threshold that we said, and also this distance is different from 0, 0, and we say that because we don't want to check these particles against itself, because if it's clear that the distance between this particle and itself is 0, so we have to say that the distance is greater than 0. Actually, you could say it greater or equal than 0. So we are sure that it's never 0. Then what we want to do is to basically fill something that we're going to send to the geometry shader. So in order to send something to the geometry shader, we simply have to input it inside the structure that we're sending from the vertex shader to the geometry shader. So let's create a new element inside this structure, which is flat, which means it's not going to be interpolated between the vertex shader and the geometry shader. I don't think this is strictly necessary though. And this is going to be for the moment a vector 3, and let's call it close particle. So this is simply a particle position, close particle position actually. So this is simply a particle position that is close enough to the particles we are currently processing. So if the distance is less than the threshold and distance is greater than 0, close particle position it's equal to other position, so the position of the particle we just examined. And we then want to break this for loop, because we are satisfied. We found a particle that is close enough. We don't need to find the closest particle, right? We are just interested to check one that is close enough, because to find the closest particle will make the algorithm much slower. Although it's feasible, but we just want to find a particle that is close enough, and then break the for loop. Cool. So now in the geometry shader, we need to get this from our structure here on the vertex shader and copy it to the geometry shader and call it the same way. So flat vector 3 close particle position. Cool. Actually, this should be a vector 4 because we want to first multiply it by the model view projection matrix, so it's going to be correctly represented on our window. So let's copy this line, the line that assigns to the GL position, so the position of this particle, the position of the particle in object space multiplied by the model view projection matrix. And then let's copy that line here. So instead of position, now we say other position. But this makes this vector a vector 4. Oh, actually we should say JIT out dot close particle position, because this is part of this structure, so in order to access it we need to access it with this syntax. So name of the structure dot element of the structure. Cool. So let's now go in the geometry shader, so close particle position, and let's do like this. Let's copy this line. So we said first we emit a vertex containing the position of our current particle. Then for our second position, for our second vertex, we want to use jit.in 0, because as we say this is an array, and close particle position. Exactly, so the second vertex is going to be the position of the particle that is close enough. Now, we say in the beginning that we are using as an output type points. Actually, we want to use as an output type line strip, because now we're going to output lines and not points anymore. So we need to copy that and put it here. Also, max vertices is going to be now 2, because we are outputting 2 vertices. You need 2 vertices to create a line. And great, let's actually check if this works. I'm pretty sure it's not gonna work, but let's give it a try. And I think it's crashing. Yeah, I think Max is crashing. Okay, actually didn't really crash, but there are definitely some errors and some stuff to fix. So first of all, I wrote threshold wrong. So actually THRASH. And this variable doesn't exist. So I'm going to create a variable called float threshold and assign it a value of like 0.1. So this will be the minimum distance that is needed for 2 particles to connect with lines. Okay, great. So here in the geometry shader, we said we're using the close particle position, then we emit another vertex, and then we enter the primitive, which means we create a line and we send it out to the next level. And the next level, actually we need to delete this line, because now we're not working anymore with points, so point chord doesn't exist when working with lines. So we need to remove this line. Okay, so let's check. Implicit cast from vec4 to vec3. Okay, this means that we are assigning a vec4 to a vec3, and I believe this is probably here in our vertex shader when we do the texel fetch. This is actually a vector 4 by default, so we actually need to say x, y, z because we want to get a vector 3. And now it works. As you can see, we are connecting particles that are closer than 0.1 together. Let's now create simply a parameter to change these, the distance threshold, and then we're going to stop for this video. So let's create a prepend param. Let's connect this here, and then let's create a message threshold. Actually, we can call it dist threshold. And then $1. Cool. Then in our shader, we can create a new parameter. Let's actually copy that, paste it one line below, and call it dist threshold. This is of type float. By default, it's going to be 0.1. Cool. So let's copy this line here to bind it now to the vertex program. So this threshold. Perfect. Now let's create another uniform float, this threshold. And actually, let's use that instead of our threshold variable. We can use these. So here, exactly. And let's now go in our patch. Let's connect a float number to that and see if this actually works. And cool, you can see that as I make the threshold bigger and bigger, the particles are going to connect with closer particles, which are farther and farther. Cool, that's the meat of the algorithm. In the next video, we're going to refine this algorithm, make it the effect look a bit better, because as you can see, we get this kind of porcupines when we make the threshold higher, and this is not exactly the effect we want. So in the next video, we're going to check how to make this effect cooler. But basically, this is it. This is how the algorithm works. It's really pretty easy. Now, if you didn't get anything of all the shader stuff I was talking about, I suggest you to check the tutorials that I put in the description of this video, and check in general all my tutorials that work with shaders, also my written articles, also link in the description, which will help you definitely to understand all this stuff and create shaders of your own. So, thank you very much for following. If you like the video, it will be cool and helpful if you put a like into it, if you subscribe to the channel, and if you really want to support the channel and get access to hundreds of patches, you can check out my Patreon and join 300 other people and get access to a lot of patches, included a cooler version of this one. In any case, thank you very much for following, and see you in the next video. Ciao!